3.4, we're going to talk again about the derivative. That's pretty much our main topic of conversation for the rest of the class. And today we're going to focus on the derivative as a rate of change. So today is going to be a little bit more conceptual compared to last time, where last class was a lot of just like, what's the rule? How do you apply it? This one's more like, okay, what are we given? What do we need to find? So there's kind of a back and forth through the rules to the concepts as we progress through the remainder of this semester. So again, this is something we looked back at in section 3.1. Recall the following ideas are all equivalent. That is to say, the derivative of a function at a point is the same as the slope of the graph at a point, which is the same as the slope of the tangent line to the curve at a point, which is the same as the limit of the difference quotient as h approaches 0 at a point. And again, right here in this lesson, we're going to focus more on the rate of change. Remember earlier in this semester, we said there was the average rate of change which dealt with what type of line? Does anyone remember? The average rate of change dealt with the secant line. And then remember that the instantaneous rate of change dealt with the tangent line. So notice here the word instantaneous is going to be omitted for pretty much the remainder of the semester, because our conversations are going to be about the derivative, aka the tangent line. So when we talk about the rate of change from here on out, we're pretty much, if it's not specified, assume it's the instantaneous rate of change, which means we'd be looking at the slope of the tangent line. So just keep that in mind. Remember that the instantaneous rate of change, or the derivative with respect to x at some point x naught, is the derivative. And this is just the limit of the difference quotient. That's, again, just review. So now that we have the derivative rules in our mind, we're going to go ahead and revisit certain concepts and certain questions using those rules to more quickly arrive at the answer instead of having to go through that computation of the limit that we have right here. So let's look at number 1. This question may feel a little bit like what we talked about at the beginning of the semester in 1.1, where you essentially have some sort of object or some sort of scenario, and you have to go ahead and set up a formula. So let me go ahead and kind of tell you what I'm grabbing onto as I read this. We're asked to write the area of a circle as a function of the diameter. So our first thing is we need some sort of formula right here to relate area and diameter for a circle. Most commonly, we think about this as a equal to pi r squared. But remember, this is not writing the area as a function of the diameter. This is writing it as a function of the radius. So our goal here is to write area as a function of the diameter d. In order to go ahead and do that, just remember the relationship between the diameter and the radius. Namely, that the radius is simply going to be half of the diameter. And that's, again, just the general relationship. If you considered some circle, let's go ahead and just kind of give us a context right here. We have this circle. We want to go ahead and consider the diameter of the circle right there. So let's say this is the center, and that whole distance right there is the diameter. So remember, area as a function of the diameter is we're going to have area equal to basically some expression with d as the variable. So, I mean, if we kind of look at everything we have right here, it's pretty easy to go ahead and figure out what that is. That is to say, the area is going to be pi times d over 2 all squared. We could simplify this a little bit. We end up with pi d squared over 4. Any questions so far? So one thing that is going to be useful as we go through this is keeping in mind our units. So for example, area is a unit, and we're talking about meters here, so technically an area is meters squared. So again, just kind of not abusing our units, being careful with that will help you just check to see your answers. So again, area is unit is a meter squared. So let's go. That was just honestly that first sentence. That completes the first part. We now have area as a function of the diameter. So that is this expression right here. So that's the answer to the first part. The next question is, how fast does the area change with respect to the diameter? So what I underlined in green there is telling us what we're needing to look for. So keyword here is fast. Fast, or how fast, is asking us about the rate of change. So if we think about this second part, what we're asked to go ahead and do is consider the derivative of the area with respect to the diameter when the diameter, here, let me change my color up here, when the diameter is 10 meters. So that is to say when D is equal to 10 meters. So this is what we're asked to find. This is what we're looking for. So just make sure you kind of take a moment. How fast? That means we're looking for the derivative at a specific point. In this case, when D is 10 meters. So this also makes sense logically if you think about, like, if you considered a circle was growing, and we had a larger diameter, notice they're not going to grow at the same rate. If you increase the diameter by a little bit, you're going to have a lot more area. So again, that's what this derivative allows us to read. If we make a slight change to the diameter, how does that affect the area? So to figure this out, what we're going to do is take the derivative. We need to find the derivative of the area. So the derivative with respect to D is, let me write it like this. We need to take the derivative of pi d squared over 4. Again, maybe just to kind of understand the notation, this is A. So this right here is A. So again, notice again, what we're finding is the green part right here is saying take the derivative of this. Remember that pi over 4 is a constant multiple. So what we can do is leave pi over 4 and then take the derivative of d squared, which is 2d. That's the power rule. Notice that remember that whatever's in the kind of the bottom of the derivative is indicating your independent variable. So that is to say d is acting as the variable here. So what we have right here is, let's see, the 4 and the 2 will simplify. So we get pi d over 2. So that right there is the derivative. And to figure out the actual, what we were asked to find, the derivative of A with respect to D when D is equal to 10 meters, well, it's just going to be pi times 10 over 2, which is just going to be 5 pi. So that's the computation. Hey, Caleb. Any questions so far? And then the unit we're going to consider is meters squared, because it's associated with the rate of change of the area. But notice meters per second, if we have just meters squared, notice that that's static. There's no movement there. So the rate of change is going to have a unit involving some sort of time. And in this case, we're going to be considering not seconds, sorry, per diameter. So basically, if we change the diameter by 1, the area is going to change by 5 pi. So again, just the units being area is meters squared, d being the unit at the bottom. So we have that. So the answer right here, I don't think it asks you to actually plug it, worry about the units in the homework, but that is something you want to be more comfortable with, especially in terms of physics. I think many of you take physics 1 and 2 in here, so units are very helpful. But the answer right here is just that 5 pi is how fast the the diameter changes with the area changes with respect to the diameter. So when the diameter is 10 meters. So that involves some ideas that we looked at early in the semester with setting up the function. And now we just want to remember when we're asked how fast, we're going to be looking to find the derivative. Derivative is a rate of change. Any questions on this example? Okay, so again, speaking about how fast, so a lot of this is going to be talking about motion. So the next page is going to go over a lot of terminology. So again, this next page, not really any examples, but a lot of just what are we asked to find and what are we thinking about conceptually when we have certain verbiage. So we're going to consider basically motion along the line, and we have these 5 words: displacement, velocity, speed, acceleration, and jerk. And we want to understand what all of those mean in the context of calculus and in some word problems that we'll look at later today. So when working with objects in motion, we typically use the variables s and t. S represents the position of an object. So this is typically going to be your vertical axis. So this will be your vertical axis. So it'll act in terms of your y's. And then t represents time. And this is going to be your horizontal axis. And what we'll be doing is we're going to consider s as a function of time. So we'll have like s is going to be equal to some expression involving t with variable t. So t is acting like the input or the x values for many of the problems in this lesson, where in standard function notation as x and y. One quick reminder that the symbol for the symbol, Greek letter, this one right here, this triangle, is the capital delta, which means change or difference. So when we're looking at the displacement, which we're just looking at the change of the position. So for example, if I were to just take my water bottle and it was initially set here at time equal to 0, and then over the course of like 3 seconds, it ended up over there. The displacement is just going to be the distance between those two locations. How do we capture that in terms of a function? Well, delta S, the displacement, is just going to be where the object ended up. So you can see we have t, and then we have some distance after or some time change. So t plus some change in time. So to figure out the actual displacement, you're going to use the function. So it's going to be t plus delta t. And then we'll have minus f of t. You could kind of think about this delta t as the h from earlier. So remember the h from earlier is some distance after our original point. Well, now just in the context of time, it's going to be some elapsed time after our initial time frame. So this is going to be like h from before. The delta t is just some distance, or in this case, I should say some elapsed time. So you can think about this as like t1, and then this whole expression t plus delta t as t2. So you can see that this is just basically the top of a slope formula. It's just the delta s. So delta s, the displacement, this right here is just, again, in terms of maybe, you may also see it, the change in position. So that's the displacement. So the average velocity, so maybe just to make it clear that we could just say AVG. So the average velocity, VAG, is going to just be the displacement. So it's going to be delta S divided by the change in time. So again, if I just kind of consider this the motion of my water bottle across the podium right here, the actual average velocity was just the change in position and then how long it took me to move the water bottle from the left side of the podium to the right. So again, you may recognize this as what we did earlier as just going to be like the change in, so this, you could think about this as f of t plus delta t minus f of t all over delta t. And again, you may recognize that delta t is acting like the h we had earlier. It's just now instead of h being some distance past x, our x value, delta t is some elapsed time after our initial time. So the instantaneous velocity, and again, I have the word instantaneous in parentheses here, is because if it's not specified, you assume it's going to be instantaneous from here on out, is the derivative of the position with respect to time. So if a body's position at time t is given by some function of t, so s equal to some function of t, then the body's velocity at time t is just going to be some velocity function, taking t as an input. That is to say, that is going to be the derivative of the position with respect to t. That's the important thing. But again, just to kind of relate it to what we already know, this is the limit as the elapsed time or delta t approaches 0 of f of t plus delta t minus f of t divided by delta t. So you can see right here that velocity, and when not specified, instantaneous velocity, is just going to be the limit of the difference quotient or the limit of the average velocity. So it's the same principles that we already built up, just using time and position instead of x and y, or I should say y and x. So, again, key takeaway, instantaneous velocity is the derivative of the position function. So you can see we have this down here below. You can see if the position function is increasing, the derivative is positive, which makes sense because it is increasing. And if the position is a decreasing function, notice that the velocity is negative. Velocity describes two things, speed and position. So we want to be careful here because there's a difference between speed and velocity. Those are not technically used interchangeably. Speed is the absolute value of velocity. So you could think about the velocity, so you could think about speed is the absolute value of our velocity function. So suppose you're in your car, maybe just to kind of make this, so suppose we're in our car and we're going 60 miles an hour, right here, so so the speedometer right here, if you think about that, it's called the speedometer, not the velocimometer. That would be weird, right? So if you think about it, whether you're reversing or going forward, if you were reversing 60 miles per hour, you're probably in an action movie or something. But this is called the speedometer. Does it have one E or two E's? Anyone? I feel like it should be one. That's speedometer. Yeah, it looks weird, doesn't it? But it's not called the velocimometer, it's called the speedometer. So again, speed is only telling you how fast you're going, not the direction. And we have correction here. It is 2, so it is. I guess it would be the speedometer. Huh? I don't know. So keep in mind that velocity will tell you speed and, I think I got a little too focused on it. I shouldn't say position, I should say direction here. Velocity tells you speed and direction, where speed is just telling you the velocity. Or basically how fast it's going. Okay, so there was a lot of terminology there. Any questions on anything on this first page? We have a few more words to define. So maybe just to kind of set us up, so we have kind of like the initial value of the speedometer over here. And if you think about how fast it went from right there to right there, you see this on like when you're looking at cars, how long does it take to accelerate from 0 to 60? How fast? So it's basically saying the derivative. So if we think about this is telling us velocity, which is the derivative of position, but this motion from the speedometer to get from right here to right here is some sort of change, and that is the acceleration. So let's look at that on the next page. Acceleration is how quickly a body picks up speed or loses speed. It is the derivative of velocity with respect to time. So acceleration is the second derivative of the position function or the first derivative of the velocity function. So we could think the acceleration is a function that takes some time as its input. You could think about it, it is the derivative of the velocity function or the second derivative of the position function, just using prime notation this time. So if you need the acceleration and you have position, you take two derivatives. If you have the velocity and you need the acceleration, you take one more derivative. And then jerk is a sudden change in acceleration. It is the derivative of the acceleration with respect to time. So I have a little joke down here. Don't be a third derivative. In other words, don't be a jerk. So if someone's being mean to you and you really want to confuse them, it's like, quit being such a third derivative. And they'll be like, they'll be confused. And they'll be like, okay, I'm leaving now. Anyway, attempt at humor, So in terms of the notation, jerk is typically referred to as a function labeled j. It is the first derivative of the acceleration function, the second derivative of the velocity function, or is the third derivative of the position function. So it's the rate of change of the rate of change of the rate of change. So like if you were looking at a car and it came to a quick stop because it ran into something very dangerous. That's my attempt at a car, very boxy, and some object that it'll run into. It'll be a pillow, so it's soft. That's worse. But that impact is going to quickly drop the acceleration, and that's captured by the third derivative. So to kind of just emphasize the derivatives in the context of Galileo's experiments with free fall, we have the equation S is equal to 1/2 gt squared, where S is the distance and g is the acceleration due to gravity. Remember that g is a constant on Earth, and these are the two constants. So you could think about g in terms of imperial units, that is, say 32, or metric units, 9.8 meters per second squared. And the question is asking, is gravity a jerk? So this is a little bit of an attempt at humor. By jerk here, I mean jerk motion. So how do I figure that out? Well, we have our position function right here. So S is equal to 1/2 gt squared. Let's kind of make this problem a little bit more earthly. So again, g will depend on where you're at. But just to make this more concrete on here on Earth, let's go ahead and do the substitution. That g is 9.81 t squared. So the position function is 4 4.9 t squared. So if we have basically time equal to 0 up here, this is some object that is going to be falling. So if this is, let's say, t equal to 2, to figure out the location here, it is just going to be 4.9 times 2 squared. And that's going to tell you basically the position. If this is basically s equal to 0, this is going to be s equal to that. So again, it's going to tell you the position. So to figure out if gravity is a jerk, let's consider what happens when we define the velocity. I'm going to need to take the derivative of the position, which is 4.9 times 2t. Where did I get that 2t from? Well, it's just a matter of using the power rule. So this works out to 9.8 meters per second. But I want to make sure I put a t there, 9.8 t meters per second. So that is the velocity. Then let's go ahead and take the derivative of the velocity. So if I take the derivative of velocity, what does that give me again? It gives me the acceleration. So the acceleration is the derivative of the velocity, which is going to be 9.8 meters per second squared. Again, remember the derivative of a constant times t. So maybe off to the side, if we were to consider the derivative of, let's say, 9x, that's just 9. It's just the same principle. We're just using t instead of x and 9.8 instead of 9. So does everyone agree that the acceleration is this right here? Is everyone okay with that? Notice that it's consistent with what we said as gravity is a constant. That is 9.8 meters per second squared. So everything's lining up. And then we have one more scenario. That is to say the jerk, which is the derivative of the acceleration. And what is the derivative of 9.8? 0. 9.8 is a constant, so it's meters per second cubed. So if we look at this right here, technically is gravity a jerk? Well, there's no jerk motion, thank goodness. Because if you realize if that was not 0, we could be walking around and all of a sudden gravity could just decide to be a jerk and knock you over. Anyway, I think it's just a funny picture, just if gravity had some jerk to it. Anyway. Question, yeah, Destiny.
So 0 will not be considered a constant?
So it is a constant, but again, because, let's switch that one. Okay, so yes. 0 is considered a constant, but it's a 0 with no, it's not going to actually affect the motion. So 9.81, it has, if you think about it as a rate of change, it's going to be a constant change in something. So this is saying there's no change in the acceleration. Let me say it again. This means that there's no change in the acceleration. Any other questions? All right, so, yeah, that was a lot of information, but any questions so far? Main takeaway of this example is the derivatives. So velocity is the derivative of position, acceleration is the derivative of velocity, and jerk motion is the derivative of acceleration. Okay, so this is an exercise of something you may find in your homework right here, number 3. So let's go ahead and look at this one. There's a little bit of a typo right here. We're not going to work with two variables yet. So this should be s is equal to 3t minus t squared. So let's use that as your position function because we're not dealing with two variables yet. We will look at that scenario later in the semester, but there still is going to be a relation to them. So that was just a little typo. So let's go ahead and put some of these ideas together. The position is a function of time, of a body moving on a coordinate line is S is in meters and T is in seconds. And we're asked three things. We have quite a bit of room, so that's good. So let's go ahead and consider part A. Find the body's displacement and average velocity, keyword average here, for a given time interval. So you can see we have T1 and T2 provided to us. The displacement was just F of, you could think about it as, yes, T plus delta T minus F of T. But remember, this right here, you could just think about this as like T2, and this is T1. So the displacement, or delta S, is just going to be F, or in this case, we're using this as our function, is just going to be 6 times 6 minus 6 squared. So that right there, just to kind of line this up, is this and this. Then we will subtract the 6 times 0 minus 0 squared. And again, to line that up with our formula, that is this right there. Is everyone okay with where I got all of those numbers and operations? Okay, so from here we just kind of simplify. So the displacement is, let's see, this is going to be 36 minus 36. And then we would end up with minus 0 minus 0. Okay, so we're saying the displacement is 0. What does that mean about the object? You got to be careful. It could have moved, but it's back to where it started. So let's think about, what did that mean? The fact that there was no displacement. Imagine my water bottle right here, started here. It is a quadratic function, so there is going to be some sort of, if we checked 3, it's going to be somewhere different. So it left, but it came back at time 6 is exactly where it started. So these are your t-intercepts, by the way. So what this means is, because there's no displacement, is that the object returned to its starting position. So that is the displacement. Any questions on that one? All right. Now let's consider I'll color code. That was the displacement. Let's consider the average velocity in blue. So the average velocity, or we'll just do V sub AVG, is the displacement over the elapsed time. So this is just going to be 0 over 6 minus 0, but this is 0 over 6, or 0 meters per second. Does this make sense? Well, it's not telling us a whole lot of information. We just know that on average, it got back to if it went some distance forward, it went some distance backwards, and basically everything canceled itself out. So this isn't really helping us describe the actual motion of the object. I had a more interesting function last year. Anyway, that's fine. We'll work through it. The numbers are fairly simple. So that's how you find the average velocity. Any questions there? Okay. Part B then asks us to find the body's speed and let me change up my colors here. Let's do some green. So the body's speed, and then we also want the acceleration at the endpoints of the interval. So to find the speed, remember we said speed is the absolute value of what? Velocity. Speed is the absolute value of velocity. So to get the velocity, I need to take the derivative of the position function. So it's going to be 6 minus 2t. Okay. So if we consider 6 minus 2t right here, this is your velocity. And to figure out what it is at the endpoints, it's just going to be 6 minus, bless you, 2 times 0, which is 6 meters per second. And velocity at 6 is 6 minus 2 times 6, which is going to be 6 minus 12, or minus 6 meters per second. So we got to be careful here, because what we have is the velocity. So the speed at t equal to 0 is, yes, 6 meters per second, but just kind of separating this right here, what is the speed at t equal to 6? 6 is the absolute value of the velocity, is also 6 meters per second. Yeah.
So what would the negative sign mean in relation to velocity?
Sure. So maybe just to kind of keep context in mind, what the question is, what does this minus sign mean? Well, something that maybe will help us understand kind of what this function is doing is, let's go ahead and just sketch it off to the side. So we're just considering, again, you can go ahead, if you set 6t minus t squared equal to 0, you would find t is equal to 0 and 6. So right here at 0 and right here at 6 are going to be your t-intercepts. Realize that this 6 minus t squared, that is a quadratic functioning opening down. And again, you can do a little bit of work with it, but it's going to be shaped like this. So I'm going to keep the domain in mind, but again, it's going to be a parabola. So it's going to come up here to some maximum, and it's going to come back down. Line that up. So that's 6. So if we think about this, we're not on its whole domain, but what that negative is saying is that we are the graph or the function is decreasing there. So just keeping in mind what this function represents, you can imagine this could be like some sort of projectile motion or something like that. What goes up must come down. So does that answer your question?
Yes.
Perfect. So that's what the negative is saying. But at takeoff and right here at landing, it is going the same speed, but the velocity is telling us the negative in the second position saying it's coming down instead of going back up. All right, so what is the acceleration at the endpoints? So if we consider then the acceleration, what color did I choose there? I think I was choosing orange. So the acceleration is going to be the derivative of the velocity, which is just going to be minus 2, right? Because the derivative of 6 is 0, and the derivative of minus 2t is minus 2. This is technically meters per second squared, keeping track of our units, the squared being our second derivative. So basically, the acceleration is minus 2 at t equal to 0 and t equal to 6, the endpoints. This is consistent with what we noticed above. Notice that like this and this were both 6, so there was no there was no variability to the acceleration of this object. So that's why those are the same. Acceleration is a constant here. Okay, and then our last scenario right here would be when, if ever, during the interval does the body change direction? So let's think, before we even do any sort of computation, think about this function right here. Think about it as an object flying through the air. It goes up and comes back down. Does the object ever change direction? Just take a look at this right here. Reading, if this is something being thrown, this part of the graph, what's it doing? It's going up. This part of the graph, it's going down. So does it change direction? It does. So how do we figure out where does it change directions? This one you can do algebraically. What would we have to find if we were just ignore calculus? We would just have to find the maximum, which for a parabola is the vertex. Okay. But think about, in terms of the derivative, what is happening there? What type of, if we consider the tangent line, what is the tangent line? It is, the slope of the tangent line is 0. So you can see right here, m is equal to 0 when the direction changes. And in this context specifically, m, remember, is the velocity. It's the derivative of the position function. The red is the position function, and then when you consider the tangent line at that maximum, it is just going to be 0, and that is when that is the velocity. So how do we go ahead and actually do this computationally? Well, for the answer to C, is what you're going to do is you're going to solve velocity equal to 0, and we'll talk about the and here in a moment. Let's just take care of that first. So let's take our velocity, which is 6 minus 2t, which is 0. So 6 is equal to 2t, so t is equal to 3. What is my unit here, by the way? Is it meters per second? It's just second. Yep, I heard that. So notice that this is 3 seconds. Okay, so if we really want to, so we're going to talk about more of like the easy way to go ahead and do this later in the semester, but what you could really think about, and I'll kind of preview this, and all we know is that there is a horizontal derivative. Technically, we know it changes right here, right? But food for thought, and what if we had some function that looked like this? You can still have a horizontal derivative or tangent line with the object not changing directions. So again, you can still have a slope of 0 for the tangent line, but the objects still not change directions. So what you should really do is check the velocity. Velocity changes. The velocity changes signs. So we have 3. And what I mean by changes signs, check the velocity changes signs from the left and right of the found t. So again, what do I mean here? What we should do is we should check t equal to 2 and t equal to 4 in the velocity function. This is also the idea of the intermediate value theorem. If that sign changes, then it actually turned around. If it is the same sign, it just maybe slowed down and then kept going. So you can imagine a car, you could slow down, come to a stop at a stoplight, doesn't mean you change directions. If you did, the car behind you is not going to appreciate it. But we do want to check that. So V of 2 is 6 minus 2 times 3, which is going to be, 2 times 2, which is 6 minus 4, which is 2 meters per second. v of 4 is equal to 6 minus 2 times 4, which is 6 minus 8, or minus 2 meters per second. So because the sign changed, we know that the object changed. And again, you could have figured that out really just kind of with our algebraic knowledge, but in general, just because something stopped, that is to say velocity is 0, does not necessarily mean it changed directions. And again, you can think about it as a stoplight. Your car stops at a stoplight, but you don't necessarily turn directions, you just pause. So you have a horizontal tangent, you have no velocity. So since the sign changed, the object changed direction at t equal to 3. Not related here, but how high was the object? How would we figure that out? How high, what am I asking for? Am I asking for a time, a velocity, an acceleration, a position? How high is a, Emma? You would plug it back into the original, which in this case would be the position function. So again, very good. Always keep in mind the context here. So if we were asked for like how high something was, that's when you would go ahead and plug it back into the position function. So still in this section we're going to analyze the graph a little bit more. We're going to look at some word problems which very much relate to that question I just proposed, and we'll just make sure that we're comfortable with like interpreting the graph of the velocity, which is the derivative of the position. So last few questions of the review for the day. So let me pose this to the class. Velocity is the derivative of what? Position. Okay, let me pose this. The second derivative of position is the acceleration. The third derivative of position is the jerk. The second derivative of velocity is jerk. The first derivative of acceleration is the jerk. And remember, don't be a... Have a great day, everyone. I'll see you all tomorrow.